Welcome. Happy Friday. Things we've got going on. We're finishing up chapter 5 with some more examples today. And then you have a post-class activity from Wednesday due today. And then want to talk about what the last post-class activity grade is. Practice problems from Unit 4 are due the day of the exam, and our last exam is a week from today, but real late, 5:30. All right. So, any questions on things coming up? Maybe, maybe we put the little cart out of your reach.
Good.
Yeah.
Give it to me.
But she already said that mousetrap on wheels wouldn't be distracting. You're not getting a hold of it.
Yeah, as long as it stays out of reach, we'll be okay. Any questions on the things coming up specifically? All right. In that case, I want to talk about that last post-class activity and the wording in it. The one due Monday. That's not how I want to look at it. Edit assignment. There we go. It is our last post-class. How do I? Okay, there we go. But what it's gonna be is actually putting, I guess, an attendance grade to that review day. With that, normal Monday's gonna be our review day where you are given that time during class to work on the practice problems and come and be able to ask questions, work on what you're needing to work on, that free time. If you come, you get full credit for that post-class activity. And you come and you're working. If you are someone who does find that you study better somewhere else, I'm asking for proof that you did work during that time. And so I can see the time you upload this, so I'm asking you upload some proof of the picture of the practice problems you've been working on, submitted in that window of partway into class and giving you a little bit of buffer time after class to upload what you worked on. If for some reason this doesn't let you upload a picture, email me. But come to class, you get the full credit as normal. Cool. It's just if you work better elsewhere, giving you a way to do so, but still prove you're working on problems. You do still need to turn in your homework at some point on that day, though. So bear in mind you have a written homework due. Make sure you're getting that to me. But it's working on problems. If you liked the normal setup, great. If you would rather work elsewhere, that's fine. Yes.
This will be the post class activity that's due.
Monday.
So like that would be for today.
Yes. Yeah. So it is labeled for today. It is the one that's called 0402 04.24. If I can close this. It's the one that's called today's. And it's called today's because I wasn't going to talk about it until today. But it is for Monday. It is the thing that's due Monday. Yes. So there is not one for this class period of one of the problems. But it is the one for today. Yes. Good clarification. Again, you show up, you don't, and you show up and you do work. You don't have to submit anything. I will give you those points for being here and doing work. It's just if you work elsewhere, you got to prove it to me. Any other? I didn't make any changes, so I hope it's okay to discard them. Any other questions on things coming up soon? All right. In that case, let's take a look at, we had that one problem in 5.8 that we needed to re-look at because it started off a particular way. And I started it by splitting, and then I got a little ways in and realized that we needed to start it by a U sub first. So we need to start by a U sub first. What U sub do you think we could make? Do 4x minus x squared. Actually, backing up one more time. My bad. The first thing we actually did before we split, or right after we split, was we completed the square. That's really the thing we needed to note. We completed the square. When we completed the square, I'll talk through it again. We note we want to complete the square because we're missing that constant term. So that can help us complete the square. We have the squared and we have the linear. We can complete the square because we're missing that constant term. Yeah, C. So I wrote it as negative x squared plus 4x. And then I factored out the negative. Yes. General things of completing the square, factor out what's in front of the x squared. Then we take b, divide by 2, and square it. What was b divided by 2 squared? 4, because b is negative 4. So negative 4 over 2 squared is 4. In the completing the square process, we add that and subtract it. So add 4, subtract 4, and now that can be factored. How did it factor? Yeah, it's x minus 2 squared. And we still have this minus 4. Last thing was distributing the negative in. We get negative x minus 2 squared plus 4 from negative times negative 4. And we substitute that into our integral after completing the square. So we get the integral from 2 to 3 of 2x minus 3 over the square root of, the other thing I did was I switched the order. Took 4 and subtracted the x minus 2. This is now, we see the square root of constant minus variable squared. And that square root constant minus variable squared generally points us to this is going to be an inverse trig integral. The problem we were running into on Wednesday was that that integral has a variable in the numerator. And all of our rules did not have a variable in the numerator. So we're talking about needing to do needing to split because of that variable in the numerator. But before we split, we should do our U sub. So For our trig integral, the trig integral, keeping that in mind, what was u? What is the variable part? The x minus 2. So then what would be du? dx, 1 dx. And so we can substitute this part out to be u. We can substitute this part out to be du. How can we get rid of that x? Hmm? What? Sorry, what was said here? Plug in the interval? Not. We don't plug in the 3 or 2 until the very end. Solve for x. We could use this part and get x by itself. So using that part, what is x by itself? U plus 2. And so I'm going to put u plus 2 in there. Solving the interval. Don't know if this was meant, but we do need to change our bounds as well.
Is that
snow?
What the frick? It was literally sunny 5 minutes ago, and it's only in this class the weather acts like this.
That's snow and it's
It makes you want to stay inside.
It's 7 degrees. That's not
Okay.
right. What's supposed to happen?
You guys live in Michigan. You're aware of that, right?
Yeah,
Okay.
no, but it's still weird.
70 degrees.
Okay.
That has a few bugs.
It's 74 degrees. Like,
Okay. Substituting out all of our u stuff. X minus 2 becomes u. Du becomes dx. And 2x, the x becomes u minus 2. Or u plus 2. Okay. All right. All of our phones will go off if there's an issue. We'll go down the stairs if there's that type of issue into the basement.
It's that kind of weather.
Sure. Our phones are probably going to go off first and tell us that we need to do that. And yeah, they're going to yell at us. But until then, we're going. How do we change the bounds? How do we change the interval? Plug them in as x. So if x is 3, u is 1. 3 minus 2 is 1. That's our upper bound. What's the lower bound? 0 from if x is 2, then u is 0. Okay. Expanding out 2u plus 2 minus 3. What does 2u plus 2 minus 3 become? Plus 1. And so I definitely was making a comment of when we do the u sub, this numerator is going to become a 1. After our u sub here, we have a numerator of 1. And so when we did this problem Wednesday, we started by splitting the integral into 2. Now that our denominator is simpler, we can split our integral into 2 and solve the 2 simpler integrals. So, splitting it up, we can split across the numerator with addition. We'd have the integral of 0 to 1 of 2u over the square root of 4 minus u squared, plus the integral of 0 to 1 of 1 over the square root of 4 minus u squared du. Somehow not giving myself enough room on this again. do this. There we go. Okay. Solving the integral 0 to 1 of 2u over square root 4 minus u squared du. Looking at just this one. I think we could evaluate that integral.
Well, it's just gonna be what one equals. Zero is gonna make it.
We can't plug it in until after we need to still find an antiderivative.
And
Yeah, we can't plug in 0 and 1 yet. We always have to get to antiderivative first. And as long as we have that integral, the integral symbol, we haven't found the antiderivative yet. If I put these in x's instead, just pretending for a hot moment we're in x's, because sometimes we see it better with the variable we're used to. How would we go about solving that integral?
Use them.
U sub, what would u be?
4 minus
4 minus x squared. So when we have a double u sub, it's just called u sub because we typically use u. We can use whatever letter we want, as long as it's not one of the ones we previously had. Where is, oh, that's my problem. So we have it in u. So let's do a double u substitution. You said we would substitute out 4 minus the u squared. That u looks an awful lot like a w. What is the derivative? You mixed up antiderivatives and derivatives there. What did you say?
Negative.
Negative 2u.
Negative. Or negative.
Yeah, negative dw is u du. So we can substitute those. What else are we going to have to do in our substitution? Oh, yes, I forgot writing down the 2. Thank you. We can change out the 2u du to just be a negative 1. We change out that denominator to be the square root of w dw. What still needs to be changed? The bounds. What's the upper bound going to be? You're plugging it into the wrong spot.
4 to 3.
4 to 3. Why here does it make sense that our bound's flipped? Because now our lower bound is bigger than our upper bound. What here indicates that that was okay? Something happened. There's a big sign, SIGN sign, overarching on our new integral.
Negative.
A negative. A negative flips the bounds. So because we had that negative dw, the bounds essentially in our minds flipped. So when we switched that negative dw, the upper and lower bound, the lower bound became bigger than the upper bound. So that's still going to be okay. That's still okay. That negative sign is essentially what's flipping our bounds. what is the antiderivative of negative 1 over the square root of w? Or how else could I maybe write negative 1 over the square root of w to help us find the antiderivative?
Negative. That would be something.
Negative w to the negative half. Okay. What's that antiderivative then?
Negative 2w to the 3 half, or no, to the positive half.
To the positive half. Add 1 and divide. So adding 1, negative 1 half plus 1 becomes 1 half. And the dividing by 1 half is the same as multiplying by 2. And we evaluate that from 4 to 3. So which thing gets plugged in first? 3. So we get negative 2, 3 to the 1 half, plus 2, 4 to the 1 half. The only thing we really could simplify here is what is 2 times 4 to the 1 half? 4. And notice again with our signs, addition's commutative, so we could have flipped this to say 4 minus 2 root 3. And that would be what would happen if this negative had gone away and we have from 3 to 4. The negative flips the bounds. That's that first half of that integral. We have our other half to deal with. I don't like it in that order. We evaluated the 0 to 1, 2u over square root 4 minus u squared. That got us a negative 2 root 3 plus 4. We still need to do this part, the 0 to 1, 1 over square root 4 minus u squared. We need to evaluate the integral 0 to 1, 1 over square root 4 minus u squared. Make that bigger. What would or this is an inverse trig. Which inverse trig is it? It's arc sine. What are some things that we see that can help us remember that it's going to be arc sine?
Where a squared minus b squared.
Yeah, the a squared, the constant squared minus the variable squared, a squared minus u squared. And the constant up top. What is a?
2.
So what is the antiderivative? Because we can jump straight to the antiderivative here. We don't need to use up.
Arc sine.
Give me a second. You said, okay. You said this.
Arc sine. Is there 1 over a in front of sine, or is that just secant and tangent?
It is just secant and tangent. That was what I was hoping to catch. We don't need a plus c here because we have bounds. So when you evaluate from 0 to 1. So plugging them in, we have arc sine of a half plus arc sine of 0. We talked about what arc sine of 0 is. 0. We can find arc sine of a half. Yeah, it's what angle will make sine be a half.
Pi over.
Over six.
Wait, no, it's
No,
sine,
pi
you're
over
right.
six.
It's 5 or 6, you're right.
Yeah, yeah. Sine, the height is going to be the smaller. So we just get pi over 6 plus 0, but ultimately pi over 6. So putting those two together, we get the full answer to our integral. I'm going to write the original integral we had was 2x minus 3 over the square root of 4x minus x squared dx is -2 root 3 plus 4 plus pi over 6. The two different pieces come together. Right. Let's might as well check our work. Graphing. So we just found, let's see here. I want to do this. 2x minus 3 over square root of 4x minus x squared dx. Nope, don't want the dx yet. And we went from 0 to 1. So what we were ultimately finding would be, if I typed everything correctly. Oh, from 2 to 3, not from 0 to 1, from 2 to 3. We ultimately supposedly found the area of this region. Which should be 1.059-ish. What did we end up getting?
That's important.
There is such a sigh of relief that I was holding in there. The integral that Desmos has the ability to evaluate and the expression we got at the end are the same. So we correctly found that area under 2x minus 3 square root over square root 4x minus x squared. And the question of what appropriate to find, I want to see the exact answer. You can always get the decimal approximation with a calculator, which is what we just did. We just compared the decimal approximations, but I want to see the exact answer. All right. Let's take a look at one other one that we had skipped. This one that's missing a dx. Okay. Any ideas what we might try? Make the denominator u. Okay.
Is relating the square roots coming
What do you mean by relating the square roots?
Rewriting it like with power instead of.
Probably not terribly. So du would be dx. And how would we get rid of the x in the numerator? Hmm? We can't split a square root. So how do we replace out the x on the last one?
We put in it.
Yeah, so we
U minus-
solve for u of x is u minus 1. So we would get the integral of the square root u minus 3 over u. Any ideas on where to go from there?
Do we not take the antiderivative?
How would we take the antiderivative there? Because yeah, that's our ultimate goal is take antiderivative.
Bringing you up and multiplying.
Hmm?
Bringing you up and multiplying by the other two and then taking into the derivative.
Okay, so you're saying write this as u minus 3 to the 1/2 times u to the 1, negative 1. And then what? Yeah. We can't do this because this is a product. And in Calc 2, you will learn the essential product rule of integrals that will handle some products better, but not particularly this one. What is the big problem we are running into? Like there is a part here that if it wasn't there, we wouldn't have any issue evaluating this integral. The square root. Sometimes getting rid of the problem is the solution. I gave a recommendation for when we make u something with a square root. I don't remember what that recommendation was. Because from here, we'd want to take the derivative, right?
So just have it by a power.
Not have it by a power, not a square root, but I did something on a previous problem where we made u equal to a square root before we took derivatives. And it was so that you might be trying to say the right thing. It was so that we didn't take the derivative of a square root. I solved for something before taking the derivatives. I got the other variable by itself. I solved for x. How would we solve for x here?
U minus root. Or no, not at all. You put u squared minus 2
You're very close.
plus 2.
Plus 2. Square it first, then add 2. And this is something I know the derivative of easier than square roots. Like, yes, we can do the square root of we can do the derivative of a square root. It's just a little bit uglier than what's the derivative of u squared plus 2?
2.
And what would be the derivative of x? 1. So dx becomes 2u du. X plus, the numerator becomes u. And what would the denominator look like? X is u squared plus 2. U squared plus 2 plus 1. And I missed something. The numerator is u. What did dx become? 2u. So combining things together, we get the integral of 2u squared over u squared plus 3. We did integrals like this a week ago, Monday. Probably Monday. What do we need to do to evaluate an integral like this? Did them in the natural log section. We have a rational. What's true about our powers? Are the powers the same? One bigger than the other? They're the same. Not subtract.
Would it be 2 as it like u goes to infinity?
As you go to infinity, yes, this is ultimately when x is really large, 2. But we don't have bounds. This could be close to 0. So this isn't a limit in the traditional sense, but we had something of if the numerator was equal or bigger than the denominator, we had to use a specific algebra step. And it's a 2-word phrase that starts with the word long. Long division. When the numerator degree is bigger or the same as the denominator degree, we can use long division to simplify it. So we have 2u squared being divided by u squared plus 3. How many times does u squared go into 2u squared? 2. What do I do with that 2 up top? Multiply it. And now what? To get the next line. Yeah, we'd subtract all of it and get -6. And this gives us, this integral is the same as 2 minus 6 over u squared plus 3. Do I know how to take the integral of 2? Yes. Do I know how to take the integral of 6 over u squared plus 3? What does that denominator generally look like? Keeping in mind what section we're in. It's tangent. It's a funky tangent, but it is tangent. Arctangent. What would be A?
No.
A would be the square root of 3. What would we do with the 6 up top? Do we need to do anything with it?
It would be over the, or it'd be in front of it, so it'd be 6 over square root 3, so then it'd be 6 square root 3.
Yeah, we can try and simplify that. But my major point is it just can stay in front of the arctan. We don't need to worry about it. We often see that constant and go, what do I do with it? You just leave it. It just stays. So what's the antiderivative of 2?
Search for you.
2u in this case. And the antiderivative of our 6 over u squared plus 3.
Over 33 arctan u over square.
What else do we need?
Let's see.
Let's see. And last up. Substitute u back in. U is the square root of x minus 2. I want to pick out one more. Hmm? First. We did that one. Okay. Let's try one last one. The integral dx over 3, not that one, sorry. X squared plus 2x plus 2. So thinking through some different strategies.
Oh, we don't need to square.
So I heard factor first, and so I'd ask myself the question of two, can I find product of 2 that multiplies to be 2? No. But factoring is going to be involved because the second thing I heard was I'm playing the square. Okay, x squared plus 2x, and I described it as I set that 2 aside because I'm just going to ignore it. So 1, factoring doesn't work. 2, we just talked about long division. But when do we use long division? When the numerator is bigger. The numerator is smaller right now. So long division is not going to work. So I see that I have a quadratic in the denominator, and trig, arctan, arcsecant, arcsine are really good for quadratics in the denominator. So I see a quadratic that I can't do any of my other strategies with. If I complete the square, I can put it in a form where I can use one of those. What is the guess as to which one it's going to be? It is going to be an arcsecant, arcsine, or arctangent. Why?
This one, I don't see any features, so let's see.
Yeah, until anything proves otherwise, there's not really any square root that might pop up. So tentative guess, tangent. But I have any idea where this problem's going. We're working it fresh here. It's gonna be tangent. So how do I complete the square?
Isn't it the leading coefficient B?
It's b over 2 squared. So b is 2. So 2 over 2 squared. 1. What do I do with that 1? Add 1 and subtract 1. This part can now be factored. How does it factor? Not 2 and 1. It's always going to be something squared. That's the reason it's called completing the square. It's going to be something squared. X plus 1 squared. And what is that? Oh, yeah, plus 1. So our new integral is dx over x plus 1 squared plus 1. Yeah, that looks like arctangent to me. What would be u? X plus 1. Making sure we don't have to do something else would be making sure du is dx, and it is. The derivatives on both sides are in 1. And what is a? 1. So this is going to be arctangent. Just fill it in. 1 over 1.
Okay.
You are correct. Yeah. Let's see. So it is arctan of x plus 1. Let's see. Not too bad on that one. But it's that recognizing of the square. All right. Done a few examples on that. So I want to talk really quickly about one last thing. And that is, there is this thing that exists. And that's basically the extent of what we often care about for this. They exist. They're important when they're important, and most of the other time they're never talked about. If I can get the right file to come up. And that is hyperbolic functions. They are the trig functions with this hyperbolic approach where the trig functions come from a circle, the hyperbolic trig come from a hyperbola. Why they're important is that they are the things that are used of if you have 2 poles with a string hanging between them, that shape that's going to be formed is a catenary, and it is defined by these hyperbolic trigs. So if you're needing to deal with something of that line hanging between 2 poles, that's where this is really important. They have definitions that come from them. The definition of hyperbolic sine, we add an h in there. So if you ever notice the sine hx somewhere, that's what this is talking about. Sine hx is defined as e to the x minus e to the negative x over 2. Hyperbolic cosine is defined as e to the x plus e to the negative x over 2. What do you think hyperbolic tangent is defined as? Just using all your knowledge about trig. It's not 1. Notice the signs do change here. So How is tangent defined? That's it. Hyperbolic tangent is the same. Hyperbolic cosecant. What do you think hyperbolic cosecant?
Well, shouldn't hyperbolic tangent be one though? Since it would be the reciprocal of cosine.
That's what I was saying is notice this. Yeah, the sign changes. They're not quite the same exact thing. No, what do you think hyperbolic cosecant is?
Negative. Cosine, hyperbolic cosine, or would it just be,
What is cosecant?
you said cosecant, basically.
Oh, sorry. Cosecant,
One of the hyperbolic.
1 over hyperbolic sine. They follow basically all the same rules. So secant would be cosine, and cotangent would be. And when we know that we can change into this e to the x thing, I know the derivatives of e to the x. I know the integrals of e to the x. When we convert into this e to the x minus e to the negative x, or e to the x plus e to the negative x, we can actually do all the calculus we had been doing in the past for hyperbolic. There are definitions of we need to work with the hyperbolic, we convert into e to the x, and we can work them out. There are similar trig identities. They're slightly different. The signs in the middle change. So, what is sine squared x? Regular sine squared plus cosine squared x equal to 1. There's a hyperbolic one that's similar but slightly different. That's hyperbolic cosine minus hyperbolic sine squared is 1. So there's similar trig rules for hyperbolic as there is for regular. Again, we can work with the regular. We know hyperbolic has a similar thing. So if we're ever needing to work with it, we know the thing exists. That's sometimes a lot of the material we need is we know the thing exists, so we can convert. So we know the hyperbolic exists. If we're ever needing to work with something where it's this line being hung between, we know we can convert. But if you're ever needing to work with them, it's the big thing. Remember, they exist. You can look them up. But that's about the extent to which we are going to talk about them. And what I'm gonna do is take the 5.9. Not having to deal with the 5.9. I'm gonna leave the 5.9 problems on the 5.9 problem that is on the written homework, but it will be graded as like a bonus point towards that homework. Okay, so you can get that extra point towards it. It's taking the derivative and of something with a hyperbolic. So my statement would be convert it into the e to the x's and take the derivative as you normally would. It's a long chain, but it's something you have the ability to do. I'm leaving it, but it will count as a bonus towards that homework. So if you don't do it, no harm, no foul. So there's one 5.9 problem that I looked at right before. Homework 11. Yeah, there's one, like I said, convert into the e to the x rules. You can do that. But again, you don't do it, it doesn't count against you. But I'm taking off the section 5.9. I will try and upload that new file for your unit problems so that you know you don't need to do the 5.9. All right. And with that, the Calc 1 materials done. Congrats. Congrats to all of you. I mean, we have an exam in a week. Thing is, yeah, I just can't get over the 5:30 time of like it's still technically over a week. But yes. Good job. We have Monday. You have homework due on Monday, so no matter what, you're needing to turn that in. Again, you have that option of coming and asking questions and being able to have that classroom environment of doing problems, and asking me things while you're working, which I highly recommend. But you can prove to me that you're doing problems elsewhere if you do better working elsewhere. Yeah. If there's any questions, let me know. Have a great few days. See you. Well, I should see you Monday because you have a homework to turn in. But for sure, see you Thursday. 5:30.